trick as before. We can take that x to the k and simplify it. So we end up then with the Riordan array. This is now a Riordan array with n changed to n minus k, still multiplying gk. So we end up with this sort of modified result here, which is equal to this. So for example, if we go back to using gk equals 1 again, use our generating function for that, we end up with this general result here, which is basically these are the diagonal terms. Oh, I should explain a little bit more about it. So if you think about it, what's happening, we're now we're looking at the n minus kth comma kth element. So for example, if you start off with k equals 0, then you'll get the n comma 0th element. Then if you change k to 1, then you're getting n minus 1 comma k. So you're actually moving diagonally upwards along the matrix, okay, and then so on. So you're going, it's not the leading diagonal direction, it's the opposite one to that. So you're going left and up along your matrix. Anyway, so applying the same result, you've got 1 over 1 minus, now it's x times q you end up with. So just for fun, let's try and see what happens with Pascal's triangle. So it's actually quite a well-known result that if you go back to Pascal's triangle and you sum up, if you sum up the anti-diagonal, so you get 1 here, 1 here again, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 plus 1 is 5. I'm running out of terms here. 1 plus 4 plus 3 is 8. So 1, 1, 2, 3, 5, 8 should ring a bell as the Fibonacci numbers. So we do indeed get the Fibonacci numbers, as we'll now show. So again, we're going to choose, where's our theorem? We're going to choose our Riordan array as Pascal's triangle. Now instead of n choose k, we're now looking at n minus k choose k, and g of k again is 1. So we apply this, it's the quotient of x to the n. P is 1 over 1 minus x, and we've got 1 minus x times q, so it's 1 minus x times x over 1 minus x. Multiply top and bottom by 1 over x, by 1 minus x, and we end up with this. And this, sure enough, is the generating function for the Fibonacci numbers. So the x plus n, x to the nth coefficient of that is big F n plus 1, where Fn is the nth Fibonacci number. So we've looked at defining the Riordan array in one way, which is sort of as a geometric series of generating functions. There's actually another equivalent way of defining them. And this point we'll answer Eric's question about. Generally, the most useful type of Riordan array is the one where Q1 is not 0, and it's given a special name. It's called a proper Riordan array in that case. And it turns out proper Riordan arrays can also be obtained by specifying how you get the next row from the row above. So this is the n plus 1th row, and we can get it from the nth row, the row above. At least for k equals 0 or more, we've actually missed out the first column. We'll come back to that later. So this gives you columns k onwards in terms of, well, it gives you columns k onwards, defined in terms of the row above. Now, I put ... here. In practice, this sequence is finite, contains finite number of terms. So we have these coefficients which are multiplying elements in the row above. So a simple example it would be if we go back to our Pascal's triangle. Well-known rule with Pascal's triangle is that for binomial coefficients, as you learn at school with the Pascal's triangle, you add the 2 above and you get the 1 below. which in terms of binomial coefficients is this relation here. So we've basically got, in this case, A0 is the coefficient multiplying n choose k is 1, and A1 is the coefficient multiplying n choose k plus 1. So AX, the function A of x, is the generating function for the sequence of A's. So in the case of Pascal's triangle, our generating function is 1 plus x. Now, it turns out that this generating function will always satisfy this relation here. So this is the connection between the Q we were talking about in our Riordan array and this way of defining elements in terms of the row above. So to find Q, if we know A, all we need to do is rearrange this. So for example, in the case of Pascal's triangle, we've got A we know is 1 plus x. If you rearrange this, you end up with Q as x over 1 minus x, which is what we had before. Now, as I mentioned, this is only for k greater or equal to 0. So we don't know what's going to happen at when this term here is 0, when effectively k is minus 1, which we're not allowed to have, because then we'd get in problems with this. So as well as an A sequence, we need what's called a Z sequence. So we also need to know the values of the Riordan array in the first column, in the k equals 0 column. So these again obtained from the row above, but this time via what's called a Z sequence, again, which looks somewhat similar. So we've fixed k as 0, and we get the n plus 1th entry in the 0th column from this formula here. Again, Z0, Z1, Z2 are from the generating function Zx, and it turns out that P is related to Z via this expression here. So going back to our example with Pascal's triangle, well, n plus 1 choose 0, anything choose 0 is 1. So we simply have that n plus 1 choose 0 is equal to the value in the row above. So in this case, the generating function is particularly simple. Z is just 1. So we end up with, okay, we also need P0. This is not specified, so we have to give a P0, the top left entry in the matrix. Okay, so we know that normally we have zeros. 0 choose 0 is 1, and most cases it's somewhat difficult to find what happens with the 0,0 case, and normally people choose it to be 1, which does help. Anyway, so if it's 1, then this gives us 1 over 1 minus z was 1, so 1 over 1 minus x, which is the p we expect for the Pascal's triangle Riordan array. Yes?
Is it clear that you can always solve for the C sequence?
Is it clear that you can always solve for the Z sequence?
Because here is for any P and Q, right? It looks like you claim that for any P and Q, you can always find the C sequence.
Oh, I think it's the other way around, that you're given the Z sequence, and then you're trying to find P from the Z sequence.
Oh, but the Q is fixed.
And the Q you've already found. So the Q you found from the A sequence by solving this equation.
Oh, okay, the Q is already there.
The Q we already know, yes.
Okay, Q is already there, and then you just make up some C sequence.
Yes. So if you're given some Z sequence, then you can then. It should be trivial to find. Well, as long as the Z sequence is finite. Is it trivial to find a generating function? No. No, if it's finite, then it is, isn't it? Because it's just the 1 plus, it's just Z0 plus Z1 times x plus Z2 times x squared and so on. So the generating function is no problem. You've got, as long as this is finite. So this is easy. This is no problem. Yeah, you'll always get it.
So it's like you have your Q, and then you define your C, and then And then if you define the px according to the second equation, right?
Yeah.
Then it should also satisfy the first equation.
The first one doesn't have the px.
The first equation. Yeah.
Oh, I see. Well, okay, when I've written it like this, I haven't actually said what P and Q are yet. So P and Q, to start with, are unknown.
Okay.
So this is just a notation. These are things that we promise to find in the future, but we don't know what they are yet.
Oh.
Okay.
Oh, okay.
Yeah.
So then you start with define the sequence.
So the only thing we start with is this property here, that we say we've got some triangle, like Pascal's triangle, which has this property, and then from that we can get P and Q.
Oh.
So as long as we've got any triangle which we can write down the row below in terms of the row above, then we can form a Riordan array or it is already a Riordan array, and we can then find P and Q using this method.
Oh, I see. So it's not for any P and Q, then just
No, you get the P and Q from this method. Yeah.
Both of them, right?
Yeah. So yeah, the A gives you the Q, and the P you get from the Z, and already knowing Q. Yeah.
Oh. But I mean, if it satisfies like the first equation condition, then.
Sorry, this one you mean? Or,
right. Then you can have infinitely many P and Q.
Oh, there's actually, well, it turns out that there's only one solution to this equation. There's only one possible Q. People have shown.
Then the second one.
And similarly, in this case, well, there's only one P. You can't.
This one is like the give a relation between P and Q, right?